rate laws. In the previous lesson, we talked about the concept of reaction rates. So we took a qualitative approach and talked about what governs the speed of a reaction. And we talked about 4 factors that influenced that rate. We talked about how you could control the rate by changing either the temperature, concentration, the particle size, or by adding a catalyst. And now we want to take a quantitative approach to that same concept. So we want to actually put numbers to these rates now. And when we do that, we will develop what is called a rate law. So a rate law gives us the relationship between the concentration of our reactants and the speed of our reaction. And it relates these quantities by using a constant, K, which is known as the specific rate constant. So in our previous lesson, we saw that the rate of a reaction will depend on the concentration of the reactants. So what we would like to do with these laws is write an expression, a mathematical formula to demonstrate that relationship. So let's take just an example equation. Let's say we've got a reaction in which one reactant is converted into one product. So a very simple reaction here. Our reactant A undergoes a chemical reaction to produce product B. Now, we could express the rate at which this reaction takes place by looking at how much the amount of A changes in a specific amount of time. Remember, rate is an amount of change over a specific amount of time. So, given our example equation here, if we had a starting amount of A, and after a certain amount of time we have less A, then our change in A over our change in time would give us our rate. It would tell us how quickly A was disappearing, how quickly it was changing into B. The deltas here, these triangles, remember, mean change in. So we have our rate is equal to our change in A over our change in T. The change in the amount of reactant A divided by the change in time T. So this rate, the rate of disappearance of A, is proportional to the concentration of A. If we have a lot of reactant, if we're starting with a lot of reactant, then our reaction can produce product fairly quickly. If we don't have much A present, our reaction is going to go more slowly. It won't be able to react A as quickly because remember, with a lower concentration, with a lower amount, there are less particles, and so less collisions, a slower rate. And we can change this from being a proportionality, this symbol here means proportional to. We can change this to a normal mathematical expression by substituting in a constant, and we're going to use the constant K. So now we've got that the rate, the change in A over the change in T, is equal to the proportionality constant K multiplied by the initial concentration of A. Okay, so our rate is equal to K times the concentration of A. Writing these rate laws will always follow this general rule. You can write rate equals K, a constant, times the concentration of your reactants. These square brackets here mean concentration of. They're a symbol. If you see a square bracket in chemistry, it means the concentration of A. Here we have change in A. Here we have concentration of reactant A. So we'll always write our rate law like this. This is a rate law. We don't necessarily need this middle part, and we will eliminate that later, but it's a way of expressing the rate, the speed at which a reaction occurs, in terms of the initial concentration of the reactants. The greater this concentration is, the faster our rate law. The more A that is available, the more collisions we have, the faster our reaction progresses. K, like we said, is a constant. It's known as the specific rate constant. And there's a different K value for every reaction. We will be either given this or we will be solving for it for each individual reaction. It's a way to relate the concentration of the reactants to the rate of the reaction. So when we know K, we can use it to give us an idea of how fast the reaction is going to go. If we've got a very large K, it means products are forming quickly, right? In this expression, if we plug in a very large number for K, we're going to get a bigger value for our rate. So a large K value will give us a fast rate value. On the other hand, if K is very small, then our rate is slower. Products do not form as quickly. So the larger K is, the faster our rate, the faster the products form in our reaction. We can also use our rate law to tell us the order of reactions. And the order of a reaction is just the power to which the concentration of a reactant must be raised to match the experimental data on concentration and rate. We're going to look at some examples here and this will make more sense. But essentially, I'm going to go back one slide. The rate of a reaction is the exponent on these reactants. Now, this rate law only has one reactant in it. You notice there's no exponent here. That's like something being raised to a 1, right? A number raised to an exponent of 1 will be that same number. So this is a first order reaction rate law. In a first order reaction, the rate is directly proportional to the concentration of only one reactant. So just like we saw before, if we doubled the concentration of A in that rate law, our rate also would have doubled. It would be directly proportional. And that defines a first order reaction. So let's look at this graph. We've got a first order reaction here. On the y-axis, we've plotted the concentration of A. On the x-axis, we have time increasing to the right. And so let's look right here. The very beginning of our reaction, we've got A is decreasing here over time, and we've got a fairly fast reaction rate. And then as we go on, as time continues, A continues to decrease, we can see that our rate here is starting to get slower. That makes sense. A is being used up. Our reactant is disappearing. And as it's used up, there are fewer and fewer molecules of it around to collide with each other and make products. So we get a rate that is slowing down. At any point along this slope, we could draw a tangent line. Recall from your math knowledge, a tangent line intersects a slope only at one point. So along this line, we could pick a point anywhere, and the slope directly at that point would tell us the rate at that time. All right. So the important things about a first order reaction, we've got a direct proportionality, which means if A is reduced by 1/2, so at some time we use up half of our initial concentration of A, our rate is now half as fast. It started very fast, it slowed down as A started disappearing and was used up, and when we have half of our A left, our rate is half as fast as it was in the beginning. We don't have to be limited to first order reactions though. We can have second or third order reactions or on to higher orders. This may occur, for example, if we have two substances in our reactants. In general, we could write this general equation for any chemical reaction. We've got reactants A and B forming products C and D, where our lowercase letters are the coefficients for those substances. For any reaction, we can write the rate by putting in K, our rate constant, times the concentration of each reactant raised to an exponent. And these exponents we will have to determine experimentally. There's no way to know them just by looking at our chemical equation. They will either be given to us or we will determine them, and we'll do an example of that in one moment. The important thing right now is to recognize that our rate just depends on our initial amount of reactant. The more reactant we start with, the higher the concentration, the faster our rate will be. Again, keep in mind that these square brackets are absolutely necessary when we write rate laws because they mean the concentration of. We cannot just use round parentheses here because that would just mean A, and we don't care about moles of A or grams of A. We care about the concentration of A, the moles per liter specifically. So we have to have the square brackets to say that. If we've got a higher order reaction, then each exponent in the rate law tells us the order of that reactant. And then the exponents added together tell us the overall order of the whole reaction. So for example, if both of these exponents were 1, the reaction would be first order in A, first order in B, and second order overall. The overall order would be the sum of those exponents. So in that example, if we were first order in A and first order in B, we would be second order overall. This overall order and the order of each reactant, again, has to be determined by experiment. It's either going to be given information for us or we're going to look at data to determine it. We cannot just guess the numbers or assume them by looking at the reaction. So let's do an example of that. Let's consider this general reaction again of A going to B. We could write the general rate law. We know that rate will equal K, a constant, times the concentration of A raised to an exponent. And this exponent will depend on the order of the reaction. Now, this reaction was carried out 3 times with different initial concentrations, and the initial rate was measured. And from this data, we can find the order of the reaction with respect to A, and so the overall order of the reaction. Here's what we're going to do. This expression tells me how the rate is related to the concentration. So if I look at my data, let's look at trials 1 and 2. In these trials, I see that the initial concentration is doubling. I go from 0.05 to 0.1. So my initial concentration doubled. Now what did my rate do? My rate increased by a factor of 4. If you need to check that on your calculator, you can take this number in trial 2 divided by this number from trial 1 to find out what factor the rate increased by. We could have done the same thing here. Trial 2 divided by trial 1 would tell us that the initial concentration increased by a factor of 2. It doubled. while the initial rate increased by a factor of 4. So what number would we need to fill in for x? When this number doubled, this number went up by a factor of 4. Try and think of that in your head. We need a number for x so that when this number doubles, this number quadruples. And we'll talk through that in one moment. Just as a quick note, you wouldn't have had to use trials 1 and 2. We could have looked between trials 2 and 3, seen that the initial concentration doubled, and again the initial rate here quadruples. We just need to pick 2 trials, any 2 trials, see how the concentration changed and see how the rate changed. Here's what we're going to do. So in trials 1 and 2, we knew the initial concentrations, we knew the initial rates. We're looking for the order. We could have written this rate law for each trial and known that the rate of the first reaction was equal to the constant times the initial concentration raised to the x power, and that the rate of the second one was also the same rate constant k. These k values are the same because it is the same reaction, times the initial concentration raised to the x power. And now, if we divide the second expression by the first, we know that rate 2 divided by rate 1 equals the second expression divided by the first. The k's, like I said, cancel because they are the same value. This would give us the concentration, the initial concentration of the second trial divided by the initial concentration of the first trial to the x power. And we know these 2 values. We know the rate of the second trial and the rate of the first trial. We know the initial concentration of the second trial and the initial concentration of the first trial. In other words, we know that the rate is quadrupling, that the second one is 4 times as fast as the first, and we know that the concentration is doubling, that the concentration is 2 times as big as the first. And now it's simple to see what x must be. We need a number where 2 raised to that number equals 4. The value for x then must be 2. In other words, this reaction is second order with respect to A. To write the full equation, we write that the rate is equal to K times the concentration of A squared. And since that is our full rate law, A was the only reactant, the reaction is also second order overall. Now, let me go back a couple. You wouldn't necessarily have to go through all of these steps. You certainly can at the beginning to be sure you're keeping all the numbers straight. But from this table, again, we could look and see that our concentration is doubling, our rate is quadrupling, and we could skip right ahead to this step. We plug in the factor that our rate changed by, and we know that has to equal the factor our initial concentration changed by raised to the x. So we knew our rate was quadrupling. That means we know that 4 must equal 2 because our initial concentration was doubling raised to the x. Once we know that x equals 2, we just plug that back into our initial rate law for x. And check your results. Make sure they make sense to you. We know that this reaction wasn't first order because if it was first order, the rate would have been directly proportional to the concentration. If it was first order, then the concentration doubling would have meant that the rate doubled. So we know it's not first order because the rate quadrupled. It was 4 times the first initial rate. So we found that the reaction was second order in A and also second order overall because A was the only reactant. We could check our work by looking at the third trial by checking our numbers against the data. In the third trial, we saw that when the concentration doubles again from 0.1 to 0.2, the rate again quadruples. Here's one more example. If we're given this general equation and told that the reaction is a second-order reaction, we could write a rate law for it, and we'll do that in a moment. We're also told that the initial concentration is 2 moles per liter, and the initial rate is 9.6 times 10 to the negative 7th. And we want to use all this given information to find out what the concentration is when the rate is 1.2 times 10 to the negative 7th. So there's a couple ways we could go about solving this. One, we can write our rate laws for these two situations. So in both cases, the rate is going to be equal to K, the rate constant, times the concentration of A squared, because we were told that this is a second-order reaction. A is our only reactant, and remember, we only care about reactants when we write the rate law. So we've got our rate equals K times the concentration of A squared, because of second order. And we're given values for 2 trials. We're given one trial in which we know the initial concentration of A and the initial rate. And we're given an additional trial in which we know the rate but not the concentration of A. So we've got four values here in our equation. We know 3 of them, so we can solve for the 4th. We plug in our rates. The only difficulty here is to make sure you keep your numbers straight, that everything that goes with the first trial stays in its right place. So for example, our unknown concentration was present when we had a rate of 1.2 times 10 to the negative 7th. So since we chose to make the 1.2 times 10 to the negative 7th rate 2, we need the concentration of A2 to be on top here. And then our rate 1 is the 9.6 times 10 to the negative 7th, and that goes with our initial concentration of trial 1, which was 2. And so now we can easily solve this for the concentration of A in the second trial. We can divide these numbers over here, take the square root of both sides to get rid of the exponent, and then multiply by 2 to get the concentration of A by itself. Alternatively, we could have broken this into 2 steps. We could have used our rate law, that our rate is equal to K times the concentration of A squared, and used our numbers from the first trial in which we knew the rate and the initial concentration to solve for K. So we'd plug our numbers for the first trial in, solve for K, and then use that K, plug it back into the rate law, the same rate law, rate equals K times the concentration of A squared, this time knowing rate, knowing K, and solving for the concentration of A. Either way, we get the same number. So we've got now a way to describe a rate of a reaction, and that is useful for us. That combined with a chemical equation tells us what is happening in the reaction. It tells us what our reactants are, what our products will be, and how fast it will occur. But the one piece of information we're missing is how that reaction actually occurs, how those products actually come to be. And for this, we need to know our reaction mechanisms. The reaction mechanisms describe to us how a reaction progresses from start to finish, all the way through. So Our balanced equation doesn't tell us the whole story. It tells us the start, tells us what the reactants are, and it tells us the end, what the products are. But if there were any in-between steps, we don't see those in the chemical equation. To give you an example, you know about the process of photosynthesis, the process that plants use to turn light into energy. Now, we could summarize this reaction by stating that carbon dioxide and water are reacted in a plant to produce simple sugars and oxygen. And that's true. That captures the overall reaction. The plant takes in carbon dioxide and water. It puts out sugar and oxygen. That would give us a balanced chemical equation, but it would not tell us the full story. It wouldn't tell us how this reaction actually happens. The in-between steps would be lost and left out. This process is actually much more complicated than that summary sounds. So to get those in-between steps, we use what's called an elementary reaction. An elementary reaction means that the reaction represents just one step. It's a single-step reaction. One reactant is converted to a product. It happens in one step. One thing moves. There's not a whole bunch of complex motions going on at the same time. This type of reaction will have only one activation energy, one activated complex. If there is one, it is one single step. And most overall reactions consist of 2 or 3 elementary reactions. For most of the overall chemical reactions that we write, they are actually taking place in 2 to 3 individual steps. And if we were to write out these series of steps, that would be called our reaction mechanism. It would show step 1, step 2, step 3. 3 elementary reactions, 3 single-step reactions that tell us what's actually taking place and in what order during our chemical reaction. When we do this, when we write out these steps, and we'll see an example in just a moment, we might find that our reaction has intermediates. An intermediate is produced in one step and consumed in another. So it would never appear in the overall reaction. It's an in-between. It's something that step 1 produces and step 2 reacts. An intermediate is sort of similar to an activated complex. It's a bit more stable and it exists for a longer time. But similar to the activated complex, it doesn't appear in the overall chemical equation. It wasn't present initially as a reactant going in, and it's not present in the final products. Like the activated complex, it's kind of like a stepping stone to get from one step to the next. So to show you what this might look like, here we have done a very complex chemical reaction. And as the reaction progresses, certain energy changes occur as our reactants are converted into products. Now, each peak represents an activated complex. Each valley represents an intermediate. So our overall equation is going from reactants to products. But that's not telling the whole story, because in the middle, in between here, we're forming activated complexes and overcoming activation energies and forming intermediates and more complexes and more intermediates and going through this set of steps to actually finally get to the products. If we've got all these steps, odds are one is going to be slower than the others. And this is going to be what's called our rate determining step. We've got 2 or 3 steps that are all taking place. and the slowest one determines the rate of our overall reaction. If you think about just a two-step process, say in step 1 we have to react 2 reactants to get product A, and then in step 2 product A reacts to make product B. Now that second step might be really fast. It might be that as soon as there is any A available, it instantaneously reacts to make B. But that doesn't matter. It doesn't make our overall equation any faster, because that step can't happen until the first step happens. It doesn't matter how fast we can change A to B. What matters is how fast we can make A. And if that step is slow, our reaction is going to be slow. Similarly, if the second step was slow, say in step 1 we produce A, in step 2 we react A, produce B. Now, step 1 could be really, really fast. As soon as we put our reactants in, we've got a ton of A. But that doesn't matter if step 2 is really slow and can only make B so fast. Our overall reaction is still going to be slow. It's still going to follow the rate of the slow step, because that is limiting its ability to progress. Let's look at this example. This is the reaction mechanism for the decomposition of nitrous oxide, N2O. So this happens in 2 steps. If we look at the third line, this last line here, this is our overall reaction. This is N2O decomposing into nitrogen and oxygen gas. That's our overall reaction. But we need the other 2. We need the reaction mechanism to show us how this actually happens, because it turns out it's not just N's breaking off and O's breaking off. We have to do this in 2 steps. In step 1, first we have to break off a single oxygen. So we have N2O, first oxygen breaks off, and then in step 2, more N2O has to run into some of that now single oxygen to react with it to make O2. So we've got 2 steps here. The oxygen would be an intermediate. It's produced in step 1, it's consumed in step 2. It does not appear in the overall reaction. It only existed as a stepping stone between the steps. So we've got our first step here. Nitrous oxide loses 1 oxygen. So now it's nitrogen gas and a single oxygen atom. That oxygen atom is going to be our intermediate. It was produced here, gets consumed in step 2. The first step is our rate determining step. Experimentally, this step is the slower of the 2. So to make the whole reaction faster, you would need to increase the rate of the first step. Making the second step faster wouldn't help any, because it's already fast. Your slow step is the first one. This is the one limiting your reaction. This is the one you would need to speed up the overall reaction. So let's have you try one problem to think about. In this reaction mechanism demonstrated below, can you identify an intermediate? We've got the first 2 lines being our elementary reactions, and they add together to give us an overall reaction. So hopefully you picked out A as the intermediate. It is an intermediate because it's produced here in step 1, it's a product, and then it is consumed here in step 2, it's a reactant. It is the only thing not appearing in our overall reaction.